looking at how we measure errors completely flips when you go from a conventional application to a mission critical application. And then what does high performance ML look like for these kinds of cases? So Onfido, what does Onfido do? So as Alex mentioned, we offer digital onboarding or digital identity verification across a range of industry segments and verticals. So today, more and more businesses are going online. This is something that has been on for a while. And it is extremely important to be able to verify a user who's trying to access a service online, whether it be opening a bank account, or whether it be renting a car, or whether it be accessing a gambling site or a cryptocurrency or what have you. There are just a large number of industry verticals, shared economies, things like Airbnb, etc. If you want to walk in and get access to that property, your identity needs to be verified. And that's where Onfido comes in. We have a suite that allows you to do that with a smartphone. And what we do is you need a photo ID, a government issued photo ID, and you need yourself. And that's enough for us to verify and validate that you are indeed who you claim to be. So in order to do this, there are 4 pieces that have technology working under the hood. The first piece is, of course, from the face, we extract from the photo ID, we extract the face and compare it to the face in your selfie. We have to unpack the document, which is data extraction, but that's not enough. That's just the first piece of it. Then we have to verify that you haven't tampered with your photo ID. So we do a tremendously powerful suite of fraud detection algorithms and services to validate that your photo ID wasn't tampered with and you are indeed the holder of the original photo ID as issued by the government. And then we have to do fraud detection on the persona, which means that you didn't grab a picture of someone from Facebook and you're claiming that you are them. So those are the 4 tech pieces, and I'll go in a little bit more detail, but one of the challenges is that we have to do this across 6,000 documents in 195 countries. So the scaling of this technology across that large set of use cases is quite challenging. So face match is a very standard thing. I think there are tons of really great methods to do this. In the triplet loss based approach that came out about 3 years ago is kind of the industry standard now, does really well. You get the face from the document, you compare it to the face from the selfie, make sure that they're the same. Then the next thing is also fairly straightforward. You extract the document, the data in the document, first name, last name, date of birth, what have you. But this turns out to be a little bit tricky because these documents have security features called holograms, which can cause interesting glare and shine effects as you collect the image. So in order to accurately do this automatically, you need to do a lot of noise suppression in order to hit high data extraction automation numbers. And then this is the more interesting part. In fraud detection, we have to look at pretty much every pixel on that license, on that photo ID that you will present. So you look at the document numbers, you have to make sure that it is an original document. Somebody didn't print out a copy and presented that copy. And then you have to look for those security features that could be either 2-dimensional features or 3-dimensional holograms often embedded in these documents. Then you have to look for the kind of deep fake things where someone could just replace a face with a deep learning algorithm and then print that out nicely and show that to you. And then, of course, you've got the fonts. If anyone tampers with the document, changes the date of birth or what have you, like a young kid who's 16 wants to access a gambling site where they're not allowed, so they just change 1 digit. So you have to have sensitivity enough to be able to find that single digit of tampering in the document. And then we, of course, want to look at every pixel because there are very interesting features in these documents that governments put in for security and to be able to validate that. What makes it especially challenging is the data is collected from all kinds of mobile devices with and without good quality. And you get documents from 195 countries with thousands of different fonts and things like that. All right. So And then the fourth thing we do is we have to do fraud detection on the user. So we have both a selfie-based fraud and then a liveness-based fraud, which means that is the person indeed there alive in front of the phone? And there is a proof of intent built in there, which means they actually intend to access the service. Okay, so that's just a quick view on Onfido and the kinds of technologies that we use under the hood. Again, this is a little bit of an introduction slide. We have about 350. We've got more than 1,500 clients across a dozen or more industry verticals that use our digital identity verification solutions. So that's about Onfido. Now I'll tell you about mission critical applications. So let's go straight on. If you look at things like search engines, e-commerce engines, recommender systems, they're not mission critical, because if they make a mistake, if a search on Amazon doesn't quite return the best result that you want, you may have maybe purchased your washing machine from a different vendor, or purchased your goods from a different vendor. Maybe you paid £2 more or $4 more. Not a big deal, right? But when it comes to mission critical systems like air traffic control or financial transactions, this is a paradigm shift. So when you look at machine learning based applications for these use cases, normally you look at average performance and you might say we hit 99% accuracy or what have you. But when you come to these mission critical systems, now you're not looking at average performance, but you're asking how many outliers were there, because every error needs to be explained. So if we let a fraudster through into a bank and allowed them to open money and do some money laundering, open an account and do some money laundering, then that will always come back to us and there is a liability associated with it. So when you use machine learning for these kinds of applications, it requires a whole set of new tools and systems that you have to build around. Another example, I think you'll also hear from Alex right after, is the autonomous driving, right? That is certainly a mission critical. You don't have room for errors there. So now that we know what mission critical systems are, let's look at an example of how could you build an ML system that could be deployed in the wild to serve a mission critical application. So here's an example of a typical ML flow. This is inference only, not the training part. So we're going to assume that training was all done and complete. Typically, you'll get some data. It could be image, video, audio data, text data, what have you. You're going to pre-process it in some form, send it through your machine learning model, and then you get a decision. If the decision seems doubtful, you might trigger an exception path. Sometimes it's manual processing, human in the loop, what have you. Or it might be a reject or some form of an exception. And if you like the result, then you take it and act on it. And in this model, what happens is most of the effort is in that central ML model and pipeline. So I'm using that model in the middle just to, while it looks like an ML model, it's actually a pipeline. There are probably several pieces in there, okay? So this is just fine for a traditional machine learning based application. But the moment you want to deploy this for a mission critical application, you need to do a lot more. So let's see what that looks like. So here the green boxes are one instance of how you can build a machine learning based system for a mission critical application that is capable of these really high performance numbers. So 4 nines, 5 nines after the decimal point. And there are 6 additional components that we propose in this particular ML system. As soon as your data comes in after you pre-process, you want to send it through a concept drift detector system. So I'm going to take you through a adversarial. So this is both adversarial attack detection and a concept drift detection, okay? So this is the famous picture you guys may have seen before, that by ever so slightly tweaking the images from the left to go to the image in the right, you can now get the machine learning system to completely be fooled, right? And so this is, a school bus gets flagged as an ostrich, or a temple gets flagged as an ostrich, or a dog gets flagged as an ostrich. So this is a place where, this is an example of an adversarial attack, but concept drift also does something very, very similar. It may not be so dramatic, but it will cause your machine learning system to silently give you an incorrect answer. So you have to build a concept drift detector system that is also capable of detecting adversarial attacks way before you get into your main system. And if your concept-driven detector system says, hey, I haven't seen this kind of data before, I'm quite sure I'll make a mistake, immediately we trigger an exception path. And either we go to manual processing or whatever exception path you may have designed into your system. If the concept-driven detector system says, this is quite similar to what I've seen, or actually it's close enough, then we send it off to an intra-domain remapping system. What this does is it makes the incoming data, it adjusts the incoming data to make it look much more like your training data. So you can either have classical algorithms that can do histogram corrections or blur corrections or glare corrections or any number of corrections, or you can have unsupervised domain adaptation that are slightly more sophisticated and slightly more capable in subtle cases. So the classical algorithms can give you gross corrections, and then the deep learning algorithms here can give you more subtle corrections. So once you take this data and apply an intra-domain remapping, you've now brought the data very close to the manifold of the training data. So now you can actually trust your machine learning model to perform well on this data. So you send it through there, and in any mission critical application, I told you that the users want interpretability. So every error has to be explained. Now, here's an example of decision interpretability. There are lots of papers out there. None of them really have cracked this problem, but it turns out if you try to solve the general problem of decision interpretability, it's a hard problem. But when you take a very specific use case, you can actually make very precise systems. Like here's an example where our system looked at this submission of a document. It's blurred out because it's PII, personal information. And it called this as non-original document present. And it said there was a screenshot in here. So we could go and ask the system, why did you call this a screenshot? And it showed us these icons here and said, because I saw these icons, I don't think this is an original document. The holder tried to submit an image they had from somewhere and tried to gain access to a service. So my point here is that in mission critical systems, if you do not build the ability to interpret your decisions, then it would be very hard to explain away when an error happens and what corrections you put into place when these errors happen. So, and again, there are three stakeholders here. One is the regulators themselves who want to know why you made those decisions. You didn't discriminate against people or something like that. The second stakeholder is the machine learning scientist to know that your models are actually learning what you want them to learn. The third is the end customer who wants to know if the machine learning system was unduly reducing their customer intake or not. So several stakeholders exist who want answers to these questions. So we covered three subsystems here. The fourth one is a confidence model. So most people take the softmax layer from the end of the network and use that as a confidence. But unfortunately, that's neither a confidence nor a probability. It is a normalizer that correlates reasonably well with confidence. Now, in most cases, when you're in a non-mission critical application, you can live with a reasonable correlation with confidence. But when you get to a mission critical application, you don't have a choice. You have to build an external independent confidence model. And this one is a tricky one. So there are two kinds. You can either build a model-specific approach or a model-agnostic approach. Now, I'll tell you that the model-agnostic approach are things you can take off the shelf, ensembles or what have you. There are a few approaches, some really nice papers coming out. And if you had the resources, you could build a Bayesian neural network with complete modeling of the weights and the uncertainties. But the model-specific confidence models are extremely powerful because they are the ones that will give you extremely high performance, but they also take a lot of custom work to build them. Now, here's an example where on the right, we're showing you where the low confidence data lies. And when there is a low confidence data in a mission critical application, you can make a decision of whether you want to trust the model or whether you want to trigger the exception path. So, so this is just I'm not teaching you how to build confidence models, but I'm telling you that an external confidence model is critical for a mission critical application. So once you've built all of these, you actually get a pretty good decision out here. Finally, you do need to understand the true performance of your system. What a lot of people do is, let's say they have 100,000 instances of something or examples of something. They sample that in some random fashion and they believe that they have a true performance of the system. But the truth is, you have to build fairly smart sampling schemes before you send it to your quality control sampling, which you must sample intelligently and through different sampling schemes in order to get a true performance measure of your system. If you just do random sampling and one population was dominant on that particular day, then all your data might come from there and it might fool you into thinking you may have either good or bad performance. But when you sample with a good idea of the underlying data model, then you get a true performance of this, of your true performance measure. Now, finally, there's a golden data set here because you will have catastrophic forgetting every time that you update the model, and you have to protect against catastrophic forgetting. And then there's the last piece is you have to have an active learning system. Anytime any surprise pops up into your system, you need to feed that back and update your models. So if you build some of these components into your deployed machine learning application, it is possible for you to achieve 2, 3, 4, 5, 7 nines after the decimal point in terms of the performance of your system. So I just wanted to give you a brief overview on what a machine learning system could look like for a high performance application. So with that, I think I will take some question and answers if there are any.
Let's just give people a sec to write some comments here. I think what I'd be curious about is, like, you know, the company's been operating for a couple of years now and was one of the early movers in the space in general. And so how have you guys seen adoption of this technology and what have been the trends that have played in your favor significantly, either on the technology side to make the product so much better so that everybody finally accepts that this should be the normal, and maybe some market drivers that would also be pushing wind in your sails?
Yeah, that's a great question. So, first of all, I think we can all acknowledge that more and more companies want to go online, right? And a great example are the challenger banks. They don't have a brick and mortar facility at all, and for them, the fraud detection piece is extremely important so that you don't get users to be able to access the banking services, especially in a fraudulent manner. And then, so what we did way up front was we built this hybrid system because understanding fraud and building protection against fraud takes some time. And so our hybrid system is a human in the loop system. So when our early first generation machine learning models were not capable enough, we had a human in the loop which they could trigger with a confidence model. And then the humans would say, oh, that doesn't look normal. And they would feed that information back to train our models. And so that human in the loop system helped us build our second and third and fourth generation systems that got progressively better. And now a very small fraction we still send to humans. And there's the humans give us that extra kick here or there, but then now our systems have gotten better than the humans. So sometimes when the human sees the automated system say, oh, this is fraudulent, they can't even see what was fraudulent until we expose certain visualizations from the models and algorithms. That's in terms of the evolution of technology and the adoption. Now, in terms of the COVID is a great example, right? Suddenly, this thing that has taken us into social distancing has gotten more businesses now reaching out saying, how can we get digital onboarding so that we can have customers that don't have to actually physically meet someone or interact with someone? And so this is just going to create a spike in demand as we see it. And as a result, there is also going to be a demand on performance. So they're going to want faster, more accurate, and more coverage. So this global coverage that I was talking about, the 6,000 documents or so globally, that's actually a difficult problem to solve. It's hard to scale these fraud detection methods across this large document volume.
Yeah. Do you, like, what have you seen with regards to the pace at which you can bootstrap a model for a new geography or a new like market category or something, which would display like significantly different data distributions from what you might have seen before? And is there some kind of transfer learning that you can apply here, or are there like domain or geo-specific models that are tuned to whatever those IDs or faces tend to look like?
Yeah. So our first generation of set of models actually trained models specifically for each geo, and they were quite good. But then in our second and third generation, we have broken up the what we call document agnostic features into a common model and document specific features into a specific set of models. So between transfer learning and multitask learning, we're able to cover the geos and offer high performance with them quickly. So we now just released late last year something that we could do with a single document sample. So we're able to cover a geo even if we had just a single document sample from a particular country or from a particular region.
And just jumping in with a question from Mel Jang. What proportion of cases typically go to exception reporting to achieve those accuracy rates in mission critical tasks?
Yeah, so it depends a little bit. So if you look at some of our verticals like facial match, etc., it is almost completely automated, right? We send almost nothing there. The algorithms are hit 5 9 6 9s after the decimal point routinely. But some of these fraud detection services that we run that look for very specific things, that number can be high. So sometimes it's a few percentage points, sometimes it's even more than 10 percentage point that we would send to manual. So it all depends on how good our confidence models are working and how much, if we see anything unusual either in the data distribution or in the image submitted, then we do send it to a human in the loop.
Got it. And another question from Alex Dilo. What's the criteria to claim that handcrafted, not deep learning based traditional algorithms succeed with domain adaptation, and what is the stop criteria?
That's a great question. So at Onfido, we have a huge combination of what I'll call classical algorithms and deep learning models, because deep learning models are capable of learning what they need to learn, but sometimes it takes a lot of data and it takes a lot of time to figure out what they need to learn. So by feeding in by combining both classical algorithms and deep learning models, we can get the deep learning models to actually learn much faster. So in many cases, we actually take classical algorithms and feed them into deep learning models as inputs for them to learn super fast. So I can't give you a generic answer, a specific answer, but generically, I think for any problem for high performance, you want to look at a hybrid. If you just go deep learning, you're probably going to require a lot more data than you need.
Interesting. Do you have any more questions for Mohan?
Nothing on the group so far.
Cool.
Sure. So I can hang around. If people have questions, they can, of course, reach out. And at Onfido,
Cool.
we're always hiring. So anyone who wants to work on really difficult fraud detection problems, do reach out to us.
And in London SF, or what offices?
London. So
London.
most of our machine learning is now based in London. So
okay, cool.
Yeah. London.
Great.
Got it. And we're posting the careers portal for Onfido in the comments section, so you'll be able to see what jobs are there.
Great. Thank you for this opportunity.
Yeah, of course.
Thank you very much, Mohan.
Okay, so I will just share this briefly. Can you see my slides?
Yeah.
Yep. Okay, great. So as Alex mentioned at the start of the meetup, we run this as non-for-profit. So our goal really is to raise a bit of funds to help advance education and research in AI for the common good. So typically when we run these events in person, everybody donates £5 to attend the event, and we distribute all this money to charities around the world. And in particular, we focus on errors in machine learning. And we've been issuing some really exciting fellowships for open source contributions in privacy preserving machine learning at OpenMind, and also for open source research as it relates to climate change with Open Climate Fix. And in the past, we've donated a lot to Code Club to basically have more of these after school coding courses for kids between 9 and 11 to learn how to code. And so we feel really strongly that it's important that the community pays it forward so that we can have hopefully more and more speakers at London.AI in the future and more technology entrepreneurs. So we do encourage you, if you can chip in a little bit and go to RAAIS.org/donate if you've enjoyed some of the content tonight. We have been forward planning a little bit through COVID with new events. So mark your calendars for the next London.AI, which is on the 14th of May, Thursday at 6 p.m. GMT. As a little preview, we'll have a talk on natural language processing and BERT models and making those work at enterprise scale for document search. And then we'll have a second talk, which is around generative design and creativity and mobile app and web app development from sketching to code directly. And then expect a couple of more events from May onwards through to June, where at the end of the month of June, we'll have our annual RAAIS conference, which will also occur online. There we'll have about 8 speakers. Half of them will be from London and half of them will be based in the US. And there we'll be covering talks from RISC-V semiconductor design, all the way to autonomous driving and biology and drug discovery using computer vision. So a really exciting set of talks there. So we encourage you to sign up on the website, and then you'll get a link to the live stream as it happens. And then just a quick reminder, if all of you could, if you enjoy the content, share it on your Facebook feed so that you can invite your friends and give them some pre-dinner conversation to have with their families at home. There'll be some really interesting talks that are coming after this. And follow us on Twitter and then on our newsletter to get announcements for the next set of presentations in the weeks to come. So with that, I'd love to welcome Alex Kendall for his talk. Alex is the co-founder and CTO of a Cambridge and London-based company called Wayve, which is building self-driving car technology. And he's also a research fellow in computer vision and robotics at the University of Cambridge, where he earned his PhD in computer vision. So Alex, big pleasure to have you, and over to you.
Awesome. G'day, everyone, and thanks for the introduction, Nathan. I want to tell you all a story about applying machine learning to the field of autonomous driving and mobile robotics. And I'm going to start by showing some demo videos and some results, and then talk through a bit more around the context about what we're building, and then finish with a deep dive into some of our latest work on future prediction. To start with, I want to show you this video, which is something we did in early 2018. And it shows a reinforcement learning system learning to drive on a real mobile robot on a car on a quiet country road. So what you're seeing here is the car is starting with doing completely random actions and essentially just injecting noise into the actuation. And this is me in the driver's seat. And whenever it leaves the lane, I grab the steering wheel and correct it. We use that feedback as a basic reward function. Basically, we get a constant reward when we're going, and then a negative reward, a negative signal when the intervention occurs. And using that, train a model-free system to learn how to drive. Now, this is a convolutional net going from the camera at the front, from the front of the car to actuating the vehicle itself, where you don't tell it anything about what the road is, the structure, the physics. It learns entirely from scratch. And you can see after just a few training episodes, we've learned a policy that can somewhat, correct and go back and forth, but ultimately it's unstable, and eventually it'll still run off the road and fail. But what's really exciting is I think this might be taken more of a given today, but if you cast yourself 2 years ago, this kind of reinforcement learning was only seen in the realms of simulation, where you needed tens of millions of data points in an Atari game, for example, to learn something compelling. And for us, to just train a system with 10 pieces of feedback, 10 episodes, to show that it could learn to lane follow was a pretty exciting proof point, indicating that this technology is ready to try and deploy in the real world. So what happens when you scale that up? Well, a few months later, we trained it on not just those 10 episodes and 10 pieces of feedback, but on 30 hours of training data, mostly of expert policy data of humans driving the vehicle around in urban environments. And what you're seeing here is the same car driving, but on roads it's never seen before. So this was a held out test area in Cambridge in the UK, and the car is driving on these roads using just computer vision alone, using end-to-end deep learning. Now, the exciting thing here is that we're seeing, what the industry hadn't seen at the time was some quite challenging, unstructured environments. It's not using a map, it's entirely driving based on what it sees, and it's able to navigate. And you can see here, it's going to go around this red truck, and then it'll slow down, give way at this intersection to the oncoming car. So we're starting to see both lateral and longitudinal control of the vehicle that is reasonably intelligent, and it can scale to the complexities and the high dimensionality of the real world. So that was all, I guess, in the early stages when we were working out of a house in a garage doing the whole startup thing in the early seed stage. But where are we today? Well, we've relocated our team to central London. We have a big headquarters in London King's Cross, and we're operating a fleet out of that, which is currently based on a retrofit deployment into a Jaguar I-Pace vehicle. So we took a photographer out one day and got some nice shiny photos if you want to have a look at our car driving autonomously in central London. But this is what our fleet is. It's a retrofit with camera sensors and other components on top of the Jaguar I-Pace electric vehicle. And we're testing predominantly in London. So hopefully that gives you a bit of flavor of the kind of technology that we're building. But I just wanted to give some context, because often when you talk to a community like this that comes from the machine learning world, they can be very surprised when they hear that actually it's quite unusual to be working on an end-to-end machine learning stack for self-driving, for robotics. But having said that, this is not a new approach, and it dates back to the late 80s, when there was some technology developed at CMU to essentially, the motivation was again to try and generalize and build a robust system that could not only be trained to drive on the East Coast, but also drive on the West Coast of the United States of America. And this motivated development of a very shallow but powerful neural network at the time to do lane following on a vehicle. I guess the modern rendition of this was reincarnated in 2016 from NVIDIA. Wayve and their team developed a system that could do lateral control, so steering control of a vehicle. And they showed it was really robust across many different appearance types, like snow, rain, different types of scenarios. And so that was a fairly exciting point that brought this back to the attention of the world. But beyond then, what we've really seen is most of the incumbent industry is really focused on the competing traditional stack of robotics, where you build a rule-based system with a large state machine that leverages an HD map to essentially understand the environment around it and drive. A common way of explaining it, at least at a very basic level, is you might think of having invisible railway tracks along a road that are governed by an HD map. So this HD map tells you what the environment's like, it tells you where signs and stop signs and traffic lights are and what to expect. And if you can localize very accurately, then you can essentially follow that map. You just need to build you need to build on some intelligence on top of that, like if there's something in your way, stop, look out for various other agents in the world, but the map can guide you how to drive. I guess the criticism of that kind of approach is that as you start to scale, it scales linearly with geographies, because you have to create this new map and maintain it, and this is many orders of magnitude more data than a service like Google Street View. So it's a lot of data and complexity to maintain as it scales. And this is the kind of system that can become quite brittle at scale as you try and plug each edge case with a different hand-coded rule. So this is really why we're motivated to build an end-to-end machine learning solution, because rather than having this brittle aspect at scale, we want to just be able to add data and re-optimize our model to fit that distribution. And I wanted to contrast robotics to some of the other machine learning fields, because to machine learning people, this might be obvious that we should apply an end-to-end machine learning system to robotics. And just like in the other data-rich fields, this will completely crush the problem with data. But there's been a few very strong trends that have only just, I think, made this possible. First one is computer vision. So what I'm showing here is an algorithm that I developed at the start and end of my PhD. And why I illustrate this is because I was quite blown away at how fast the community was able to develop computer vision technology just in a couple of years. And it's gone far beyond anything I did in my PhD. To be completely honest, it's computer vision is really incredible today. And in 2015, when we worked on SegNet at the University of Cambridge, this was the first time an end-to-end deep learning system was applied to autonomous driving and semantic segmentation. And that was exciting, but as you can see, it was still quite noisy and not really robust enough to drive. But at the end of my PhD, I was able to develop a system that learned semantic segmentation, depth estimation, and optical flow. So that's semantics, geometry, and motion from a single representation. And that's what I think gave me the confidence to say, look, we may not need an HD map, but we can make driving decisions based on what we see because of that rich representation with computer vision. The next trend, I want to contrast robotics to some of the other industries because the other fields, because we've seen, in 2012-15, computer vision went through a step change in performance through end-to-end deep learning. I think NLP did the same from maybe 2015, 2019, and speech perhaps a little bit earlier than that, but all these other fields have been completely revolutionized by deep learning. A really good question to ask is, why is this not true in robotics? So if you go to CVPR or NeurIPS or these kind of conferences, you'll perhaps laugh at today if you don't use end-to-end learning. But in robotics, that's not true. ICRA for the last few years has still been yet to, I think, fully adopt machine learning. Now, why is that? Well, in my opinion, I think there are a few reasons. Firstly, data is so much more difficult to obtain. You don't have a static data set like you do with ImageNet for computer vision, for example. You don't have this train and test paradigm where you can just optimize your models. You have this changing distribution, this exploration problem of states within the real world that is much harder to measure with metrics and much harder to get substantial amounts of training data. There's also the safety problem. You can't sit in your fancy office desk and just work on this. You have to go out in the real world, collect data, and simulation just isn't there to be a tool to do this on its own. So I think all of these reasons really add up to push robotics maybe a decade behind computer vision and NLP. But in my opinion, it's just inevitable until this kind of revolution happens to robotics too. And that's what we're really trying to push at Wayve. Finally, I think there is another trend that's really moving away from edge compute and moving to training compute. A lot of self-driving cars from previous generations had crazy amounts of compute on the vehicle. We're talking a data center with 8 GPUs running a 4 kilowatt system in the back and the boot of the car. Now, our vehicle has a very lean amount of compute running only a couple of 100 watts. But in contrast, we leverage ridiculous amounts of training compute. And I think that's really where the industry is going. Maybe one day we'll be able to have a smartphone level of compute to really control enough intelligence to drive a car. I think that will be possible. You can draw many comparisons to this point. For example, if you look at systems like AlphaGo or the OpenAI Dotabot, these were trained on tens of thousands of GPU years, yet when they were deployed, often on a simple CPU. And so I really think we're moving away from edge compute and more to training compute. And that's that sort of level of compute is really enabling a lot of these robotics applications. But it's a really key point for scale, because when you get to this point, you can really leverage hardware at scale and deploy with little friction to many robotic devices. So that gives a bit of an overview, albeit a very brief overview about how we're thinking about self-driving and maybe some context for those of you who aren't deeply familiar with the field. I just wanted to finish by doing a deep dive into some of our latest work. It's something I'm quite excited about, and it's all about predicting the future. This is a key part in building a driving intelligence. As a field, we've made a lot of progress in perception and also policies and control, but predicting the future is a really core task. In fact, many neuroscientists argue that it's a core aspect of human intelligence. If you can understand and predict dynamics, then that means that you can really understand, or have an intelligent understanding of the scene. And that's and we think that's really important for driving. But unfortunately, the industry isn't quite there in terms of performance. And so this is a step in that direction. So let me share this work with you. So let's consider this scene. This animation going up to this this intersection. If you were to predict the future, you could do many things. You could turn left, you could turn right, you could go straight. One of the challenging things about predicting the future is that our training data only ever gives us one sample. So you could argue with physicists, whether the world is deterministic, but at least with the sensors we have on our robots, we have a partially observable world. And so if we knew everything about the world, we could, maybe there's no free will, maybe we could predict where the car's going to go. I'll leave that debate for another day. But at least in this situation, I think it's fair to say the car could go any of these directions. But when we get training data for this, we only get training data of the car going in one of those directions. And so it's an inherently multimodal and probabilistic problem. But unlike other multimodal probabilistic problems, a common one is medical image segmentation, where you have an MRI scan and you have multiple expert radiologists label it, and then you have each of the multimodal labels corresponding to a given data point. That's much easier, but in this case, you only ever get to see one future. And so what we've built is a model that can predict multimodal futures that are plausible and accurate. And so here you can see us predicting into the future what might occur going forward. And you can see if we sample our model once, we get a turning left, another time go straight, and another time turning right. And each of those different samples gives a different mode of the future distribution. And this is quite exciting to us because we're able to predict not only individual agents, but the static scene and our dynamic behavior all jointly in one future prediction. Just to contrast that from previous work, so previous work often from perception will understand where each agent is in the scene, like a car or a pedestrian, and it'll individually predict their action. That falls over when you think about a situation like merging or four-way stop signs or traffic or roundabouts, because how you behave affects how others behave and vice versa. So it's important to jointly predict all of these things together. And that's what we've built. So to quickly run through the architecture, we can encode previous frames in the video into a representation and encode a temporal representation. This could be a recurrent neural network. In practice, we use an autoregressive model. We then take this representation ZT, and the natural thing to do might be to unroll it into the future with a recurrent model and then train it to predict the future. Unfortunately, that doesn't work because I mentioned there's multi-modes in the future. If you just try and unroll it, you're going to fit the data very poorly. So what we need to do is give the model an understanding of that distribution. And we do this by creating two distributions, the present distribution and the future distribution. The future distribution, we can use our privileged view of the future at training time, so we can actually look at how the future unfolds and create a distribution based on that. And the critical thing about seeing that privileged information at training time is we can tell the model to unroll that future, not any future in the distribution, but that exact future. And that allows us to apply the actual unrolled future that we see as a training loss. Because you can imagine if we get the model to unroll any given future, but the future we see is a different one, we can't apply the loss directly because it doesn't make sense to minimize that because it's a different future. So by seeing that, that unrolled data, that privileged data of the future, we can guide the model to predict the right point in that distribution. But then of course at actual inference time, we don't have access to the future. So we also train a present distribution, which is conditioned on ZT. And that present distribution is trained, we minimize the divergence between that and the future distribution so that we try and model the future with only understanding knowledge of the past. Now, given that, the neat thing is that we can then sample at test time and sample different futures. And then of course, apply those futures to leverage and improve the control of our autonomous vehicle. So this is the model. The paper link is below if you want to read more details, but it's all about using the privileged future information that we get the single unrolled future to learn a distribution. And the neat thing about this is despite only having one future for each data point, we can only see one example of the future each time, we still learn this multimodal distribution. And let me show you some results just to finish. So here's another example going through a four-way intersection, and we also see a stopping mode. The neat thing is that I also mentioned the futures have to be plausible. So not only do we get accurate futures, but we also get plausible ones. Because if we advance a little bit in the future in this video and then generate futures again, every sample is only turning left because the car's already started to turn left. And so, and and so the other futures no longer make sense. So it's not only accurate, but plausible futures that we care about. This one's interesting because it shows multi-agent interaction. And here we're predicting the future in semantics, depth, and flow space. And in the middle column is showing the uncertainty of our model. And you can see that we get future predictions around unprotected right turn, where we sort of nudge forward, we turn right, or we even just forget it and go straight. And this is neat because it shows some multi-agent interaction that we're able to capture from our data. And then finally, here's another one where we either just stay stationary or pull away. And you can see that, again, we're able to capture this multimodality and understand different dynamic scenes in the different dynamic agents in the world. So this is, I guess, initial work, but it's really exciting because I think what I've shown is we can build this representation that can understand the multimodality, understand rich semantics, motion, and geometry, and also understand other agents. Of course, there's a lot of work to be done on this representation to further scale it, but it's a key building block, I think, in a learned driving system. So to conclude, I just wanted to finish with, I guess, wrapping up why we're doing this. This is really the crux of what we're building. It's trying to move the mobile robotics industry away from reliance on HD maps and copious amounts of sensing and really high capital costs to get this technology to market. We think that this technology is really what's going to scale us, and it's clear that others have got to this technology to the first city, but I think this is what's going to get us to 100 cities, and our aim is really to scale and to get to 100 cities first. I also think it's important to note that this really simplifies the engineering, working on an end-to-end machine learning model, but we really care about getting together the right group of highly skilled people to be able to do this. So we don't want to build out a really bloated 1,000-person team, but keep a really lean, highly skilled group of engineers around this problem. And I think that's what's going to really take us out of this trough of disillusionment with self-driving and really crack this problem for everyone. So, of course, the credit really goes to the fantastic team that I feel lucky to get to work with. And here's a photo. It's actually 6 months old now, but this is from our headquarters and workshop in central London. But a big thanks to all of them for the work behind this. And there's some links at the bottom if you'd like to read more. We've got a blog that talks all about our work with some of the academic publications behind it. And we're really looking to add a few key people and experts to our team. So if you're interested in this mission and passionate about this technology, do drop us a line at the email below. But other than that, I'm happy to take any questions, and thanks very much for inviting this talk. Cheers.
Super, thanks a lot, Alex. Yeah, really fascinating work. We've had quite a few questions. So we got one from, from Roland here. He says, how would you compare US efforts and resources like Comma AI and Tesla with European ones and maybe some of your peers?
Yeah, sure. I think the US has really been, or this industry has really been commercialized, I think, out of the DARPA challenges, which were organized by the US back in the mid-2000s. And I think that really kickstarted things. And we've seen a large amount of capital, venture capital largely invested in the industry. I think there's no doubt that that's very substantial in the US and also in other places like China. I also think that Europe has the side effect of that is that there's also a very correlated approach between many of the teams in for example, in Silicon Valley, because they've all come, all the technical literature. The side effect of that is that there's also a very correlated approach.
Alex, you might want to mute your Facebook page yet.
I don't think I have it open.
Okay. That was me.
Oh, never mind.
Sorry, I was just going to say that it's interesting when you look at these teams, online somewhere there's a family tree of the DARPA Challenge leaders that all were prolific in all of these companies. And I do think there is a thought bubble happening over there with similar approaches. The two that you name dropped, I think, do start to break out of that thought bubble. But what we have is I think, a different problem set. Certainly, looking at urban driving is different from, I think, the focus on highway driving in the US and higher speed driving. If you think about London as a problem set, most roads are 20 or 30 miles an hour. There's a lot of multi-agent interaction that's needed, and that does drive approaches like ours compared to the classical stack, which do really well on the American freeways. So there is this different problem set. There is a different collection of people working on it. a different bubble to work in, and I think that is unique here. And interesting, I'll leave that there.
So we have another question, which is, how are you balancing imitation learning with reinforcement learning in production? And what's your approach to achieve safe, predictable RL decisions?
Yeah, I think creating a curriculum and the distribution of data and then the learning signals on top of that is one of the hardest problems. In some ways as an industry, we've gone from feature engineering to model architecture engineering to now data engineering. But how you leverage expert policy data on policy data and bring all of these things together is hugely challenging. I mean, we collect every month thousands of hours of on policy and expert policy data, and combining those and learning signals is something we spend a lot of time working on. I mean, the kind of learning signals that we can use are the self-supervised ones from motion and geometry and future prediction, the supervised ones from semantics and in terms of perception. There's the supervised ones in simulation, some work on our website talking about how we approach sim to real with generative modeling. There's clearly when you have safe driver intervention, you have the reinforcement signal of that intervention. You also have the corrective action, similar to the Dagger algorithm, if you're familiar with it. So you have that corrective action, which is supervised. And then from the expert data, you also have a supervised approach. So combining them, and it's all in, I guess, a offline policy learning setting. Combining these signals is really tough. I don't think it's something that the machine learning field has really been well motivated to look at in depth to date, but we're seeing a lot of exciting work coming out of there, combining it. But yeah, it's a hard problem, and I won't go into any more details than that at this stage, I'm afraid.
Yep.
And a quick question from Simon Greenman on how do you deal with the edge cases? So I think he's citing the typical cardboard box that would randomly swip into a lane. Do you stop the card? How do you deal with those?
Yeah, this comes back to the data distribution, right? So if you uniformly sample epochs and run them over and over again, you're going to really suffer in those edge cases. So you've got to, I think, be very smart about how you identify it. The natural distribution of data is natural for a reason, but having said that, you need a large volume of data to be able to capture some of those edge cases. So if you get enough data and you sample it correctly, then you can give your model that information. And if you pull out things like uncertainty or predictive error metrics, and you can measure the sort of epistemic measures of uncertainty to allow to target that, then that's fantastic. The other thing I'd point out too is if you can give your model the right compressed representation that can factorize out different components, if you see roundabouts in the rain and these card boxes in the sun, then can you also deal with roundabouts in the sun and these card boxes in the rain? And can you disentangle these things? So I think your state representation is very important. And then coming down to the distribution of data, not just the state action distribution that you have access to. I think you've got to really sample that very cleverly.
And without wanting to obviously reveal your trade secrets or your entire roadmap, but what does a company like Wayve look like in the next 2 to 3 years?
Yeah, I think there's a lot of exciting things yet to come. So what I was able to show you at the start of this presentation was our small Twizy vehicle driving around in Cambridge. But seeing these iPaces drive around in London, and if you live or work around King's Cross after coronavirus, keep an eye out. They're on the roads all the time. And actually deploying this technology without an HD map, I think in an urban environment is a big leap for the industry and something we're really excited about. The natural road to an autonomy product is an interesting and complex one, and not one we're talking about publicly at this stage. But we're completely set and excited on developing our safety case and getting this in the hands of the wider society as soon as we can. There are many routes to that that we're very excited about.
Cool, awesome. So I think if any of you have some more questions, you can just drop them in the video channel here, and then we can always ping Alex a bit later, or you can maybe take them if he's going to plan on hanging around. But thank you so much, Alex, for taking us through that. It's a great presentation.
No worries. Cheers, everyone.
I'd now like to introduce Chris Lovejoy. He's going to cover topics in medicine because he comes from that domain. He's a medical doctor, senior house officer in the NHS, and former clinician, data science, and technology lead at Cera Care. which is a London-based startup. And he also trained in machine learning at UCL. In particular, he'll be presenting around some recent work that he and colleagues have published, which really looks at clinical applications of deep learning in medical imaging and studying some new findings that we can infer from those by looking at them as a group. So over to you, Chris. Thanks a lot for joining us.
Okay, thank you, Nathan, for the introduction. So, as Nathan said, my name is Christopher Lovejoy. I'm a junior doctor doing research in applications of machine learning in healthcare. And today's talk is going to focus about a recent research study that myself and some colleagues did, where we appraised different studies that compared AI performance with clinicians, and also touch on some of the wider questions around the role of AI in healthcare and the kinds of things that this research raises. So to begin with, I just wanted to share a few of the kind of perspectives at the moment on the role of AI in healthcare. So on one side of the fence, we have a lot of prominent figures in AI and in machine learning saying things along the lines of, in the top left here, Geoffrey Hinton saying that he thinks radiologists will be replaced in a few years' time. He said this, I think it was around 3 or 4 years ago. So, and then in the bottom right here, this is a blog post written by Vinod Khosla, who's a prominent investor in Silicon Valley. And essentially his conclusion or his thoughts were that by around 2035, he thinks about 80% of doctors will have been replaced by AI. And then on the other side of the fence, we have people making the point that perhaps AI is going to be more about supporting doctors. Maybe it's going to be doing a lot of the repetitive tasks that doctors have to do and free up their time to do other things. So on the left here, this is a book by Eric Topol, who was one of the co-authors on the paper. And in this, he makes the argument that AI will enable us to have the time to foster the doctor-patient interactions and ultimately kind of rehumanize healthcare, is the argument that he makes. And on the right here, there's a couple of research articles also making similar sorts of points. So the purpose of our study was to critically assess the studies that have been published so far and see what sort of claims they're making, seeing how valid those are and how much the kind of science supports those, what sort of methodology they followed. And we asked 3 main questions as part of this study. We asked what types of studies have been done, how well were they done, and how well were they reported. So in terms of the first question, what types of studies have been done? To give a little bit of context for those not familiar, the gold standard level of evidence in medicine is the randomized controlled trial. And basically what this involves is you take a population, you divide it into 2, you do 2 different interventions, and then you measure the outcomes and compare those outcomes. So in the context of applying an AI algorithm to healthcare, on the screen, this is an example of a study that has been done, which was the group took some people who needed colonoscopies, which is where you put a camera into the colon to try and identify polyps that might be cancerous. And what they did is they had a human performing the colonoscopy and looking at these lesions, but then in a separate room, they had either a doctor or an AI algorithm reviewing the images at the same time. And if the doctor or the second doctor or the AI algorithm flagged up a potential lesion, then that would get fed back to the doctor. So the person performing the colonoscopy didn't know if it was coming from an AI or a human. They then measured the rate of polyp detection and kind of reported the performance. And in that case, it was the case that there was more polyps detected by the AI. But essentially, this is very much the gold standard because you're taking out any of the potentially confounding variables. You're directly comparing 2 things side by side. And kind of more broadly, you have prospective studies and retrospective studies. So retrospective studies is where you are training your model on data that already exists, and then you're testing it on data that already exists. Whereas prospective is you train your model on the data that already exists, and then you collect data in real time and analyze the performance of the model on that. So an analogy might be, you might train an algorithm on, let's say in the stock market, you might analyze on all the existing stock data that you have. And if it was a retrospective study, you would then test that performance on the existing data, although obviously you'd probably keep a subset of it apart to try and test the performance. Prospective would be testing things going forward. And you typically see a drop in performance when you go from a retrospective study to a prospective study. And there's several examples of this in healthcare. So there's a prospective study for breast cancer screening, which then, when it was done prospectively, didn't see the same positive impact, and a similar sort of study in childhood cataracts as well. So when we then came to look at what studies have been performed so far, looking at deep learning in healthcare, we found at the time of our study, so this was closed last year in June 2019, we found that at that time there were only 2 randomized control trials, and there were 9 prospective trials out of 81. So now there are more. So as I understand, to my knowledge, there's now up to 6 randomized control trials, which are shown in this table on the right. But ultimately, it kind of points towards relatively weaker evidence to support the kind of abilities of these AIs and the comparisons with clinicians, and kind of points towards just being fairly early in the development of this kind of research field. And I think it makes sense because obviously deep learning is a relatively recent field. There's always going to be a lag once you have that technology to then build algorithms to be used in healthcare and then run those trials, etc. So probably with time, I imagine this will catch up and we will start to see more and more randomized control trials and prospective trials going forward. But ultimately, that's kind of like a reflection of the current state of affairs. So the second question was, how well were these studies done? And there were 2 main weaknesses that we identified in the methodology of studies that have been done so far. The first of those was that, on the whole, the clinician control group tends to be quite small. So the median number was 4, the interquartile range was 2 to 9. And some studies also reported non-experts and kind of averaged the performance between the 2. And I think one reason why we're not seeing a huge number of clinicians in these studies is the fact that it's very time consuming to recruit clinicians and to test their performance, because when you're doing deep learning studies, you're typically looking at a very large number of samples. But ultimately, it can weaken the conclusions because you can expect a degree of variation within clinicians, and particularly if you kind of dilute the performance with non-experts, then that's going to affect the ability to make claims of the AI being kind of comparable or superior to doctors on the whole. And the other thing that we found, so we used this tool called the Probast, which is a tool for assessing the risk of bias in studies that are trying to perform diagnosis or prognosis. And essentially, it's a list of questions around the different methodology approaches that were used in the study. And we found that of the 81 studies, there were 58 that were ranked according to this as having quite a high risk of bias. And particularly poor performance was on the analysis section. So there's a couple of sample questions from the analysis here on the slide. And the ones that we typically saw they didn't perform well in was sometimes the sizes of the data sets weren't huge, and they often didn't really take measures to prevent overfitting or kind of comment on the risk of overfitting. But this all just points towards the quality of the study designs not being extremely high, and therefore there being quite a high risk of bias. And one potential kind of contributing factor to this is because AI being applied to healthcare is quite an exciting field. Maybe there's a kind of degree of the publishers wanting to publish these kind of papers and maybe lowering the threshold a little bit, or maybe just the methodology is not kind of fully standardized yet because it's still a relatively early stage in the field. So the third question we asked was, how well were the studies reported? The first finding was that using a tool to assess this called the tripod, on the whole, the adherence to the reporting standards was quite low. Essentially, this is similar to the Probast. It's a checklist, but this one looks more at the study methods themselves. Sorry, the reporting of the study. And there is a bit of a caveat in that this tripod system, this tripod checklist, was initially devised for regression models. So it tends to kind of lean a little bit towards that, and some of the questions are not super relevant to deep learning. But we did account for that in the study. So for example, there's some tripod questions about the predictive variables, which actually in deep learning of medical imaging is less relevant. But what's happening at the moment is the research group that devised the tripod are currently devising one specific to machine learning with the hopes that that will kind of standardize the research methodology approach and the kind of reporting standards in these kind of studies. And then the second thing that we found on the reporting point of view was that the code and the data that was used in the study tended not to be available. Obviously, there's a challenge when you're doing kind of AI studies in healthcare because it's a relatively novel paradigm for healthcare to have code as being a kind of central part of the study. And there is understandably some resistance to want to share your code, because if you're an organization that is running a study with the hopes of commercializing that, then you might not want to share your kind of intellectual property. But one of the kind of fundamental tenets of medicine is the reproducibility of the studies. So we would like to have code and data being available so that somebody else can theoretically recreate that and just make sure that they find the kind of same sort of outcomes. So in terms of just kind of drawing a few conclusions on this study, I think the main takeaway is just the fact the state of research is relatively early of applying AI to healthcare. We still need a lot more studies going forward that are prospective and are randomized controlled trials. And those studies, we need kind of good quality design of the studies and also reporting standards. And hopefully with new guidelines and more guidance on this, then we will see that kind of improvement in that quality. I think there are a small number of cases where we can confidently say that AI performs better than doctors, but often it's in the case of AI in a role that assists doctors rather than replaces them. So for example, the polyp detection algorithm I mentioned earlier, in that case, it is the case that the AI as a second screener of the polyps performs better than having a doctor as a second screener. And probably that's due to the fact that the kinds of things that the AI is good at picking up is slightly different to the doctors. And it was the case that when they interrogated it, it seemed to be that the kind of smaller and flatter polyps are the ones that the AI was able to detect. But ultimately, we should just kind of strive to be careful and like quite objective with how we explain the current state of affairs. We found that in the 81 studies that we looked at, 23 of them claimed superior performance to clinicians, but they were retrospective studies and they didn't mention caveats like the need for prospective testing. And some of them said that it would now be appropriate to kind of do clinical implementation of these algorithms. And if we do allow ourselves to kind of use overpromising language without the appropriate caveats, it can contribute to hype and perhaps unrealistic expectations on the current state of affairs of applying these algorithms in healthcare, and maybe potentially mislead the media and the public to some extent. So that's it's an important consideration to make. And the other thing as well is about the way in which we frame the question of is it kind of AI replacing doctors or is it going to support doctors? Right now, it seems that the studies that are doing well are ones more in a supportive role. That's not to say that AI isn't going to be able to do some tasks that doctors kind of currently do as a primary task. But obviously, despite this, I know that generally the findings of the study were fairly critical. I would personally say I am pretty optimistic about the potential for AI to be used in healthcare. I think it's only a matter of a year or two before we see lots of exciting applications of AI in narrow domains within healthcare. I think it's just a reflection of the state of affairs, which is that we're at a relatively early state kind of within this research field. And hopefully in a year or two's time, we'll see a lot of these kind of narrow domains being supported by strong evidence and better patient outcomes as a result. Just to close, a couple of references. So the top one is the reference to this original paper. Twitter, one of the co-authors, Eric Topol, is very active on Twitter and shares, if anybody who's interested in AI studies in healthcare is very active. It's a bit of a treasure trove on like what's going on right now. There's a blog here that I'm a big fan of by a radiologist and a PhD student called Luke Oakton Rayner, and also share a few articles about machine learning in healthcare as well on my personal websites. So thank you all for listening, and if there are any questions, I'll be happy to answer them now.
Chris, thanks a lot for this presentation. Just jumping in with the first standard and obvious question, but if the community wants to help or get involved, what's the easiest way of doing so?
When you say community, as in?
Yeah, sorry. So the usual members who attend London.AI.
So I guess, yeah, it depends. It depends what your background is. If it's more of a kind of technical background, then probably the best ways are, I think a lot of these studies ultimately will require collaboration between clinicians and between people who have deep understanding of the kind of AI technology behind them. Because one of the issues is obviously if it's a clinician leading the study, then they need to have, they're not going to have the appropriate insight into the ML side of things to fully take into account risks such as like overfitting and just the different aspects of the study design from a machine learning point of view. And likewise, someone purely with a machine learning background won't have a strong insight into the clinical aspects and some of the nuance around that. So I think fundamentally it is a collaborative effort. So the key thing, I think, for establishing that collaboration is if there is anybody who wants to collaborate on these sorts of projects, then just looking out for opportunities at research groups at like the universities nearby or local hospitals, and trying to see who's active in that space and just setting up collaborations with them, I think is probably the best route to take.
So, Chris, like in the last, say 12, 18 months or so, the US FDA has issued approvals for maybe 4 or 5 or so medical imaging products, ranging from kind of the broken wrists or I think something to do with cardiology, and perhaps another one to do with ultrasound. Have you seen post FDA approval an uptake in adoption of these tools in clinical practice, or is this like holy grail of FDA approval just the tip of the iceberg with regards to driving adoption?
Yes, so the current kind of level of evidence that's required for FDA approval is the retrospective studies. So you don't have to have a prospective validation or a randomized controlled trial, like I mentioned. And so there are a lot of things that have been approved by the FDA and that have had uptake on a pretty wide scale, and are not yet prospectively validated. And I think the kind of key thing here, and what's slightly tricky, is obviously we don't want to kind of stifle innovation and stop people from developing these algorithms and implementing them. But we also obviously don't want to risk patient safety. So there are a lot of cases where, yeah, we have these algorithms that have been developed and they're now kind of in use. But I think in those cases, it's always done in a fairly kind of safe and cautious way, and always with a look to then develop prospective validation, because once it's got that approval and then you're doing these studies in the real world, you'll quantify the performance and then report that. And I think that's like a really key part of it, is that made for that. But also when you look at a lot of the tools that have been FDA approved and are in use, they are typically more in roles such as like triaging, for example, where they're not having a direct decision, in a sense that they're not making a diagnosis of one thing or another. They are maybe triaging a scan. So for example, Viz.AI have an algorithm that looks for the presence of a stroke. And the idea of that is it flags that up and will then kind of alert clinicians to potentially save time. And there's a similar algorithm as well for triaging chest x-rays, so that chest x-rays get reviewed more quickly. But in that case, if you're leading, the risks of like mis-triaging that are relatively low, because if you triage a scan, it gets reviewed earlier, and actually there wasn't really anything on it, then there's not really been any harm kind of come as a result of that. Whereas if it was something more about maybe making a diagnosis and then there's not a second person looking at that, then there's like a higher risk there. So
yeah, and then one of the topics that that Luke, whose blog you listed on your talk, is mentioned in the past that I thought was quite interesting, was the kind of broad quality, so to speak, of the labels that are usually added or appended to images that are then used for training machine learning models, especially in computer vision. You know, some examples of researchers appending labels to images that you couldn't derive solely from those images, and so you get a model that's predicting something, predicting conditions you can't diagnose from the visual data alone. So to what degree did you look at, or do you have a sense of whether like labels that that clinicians are using in these studies are actually of high quality, or if we still have big problems there and should be enforcing standards?
Yeah, so it's not something that we looked at specifically in this study. I am aware of certain data sets in particular, kind of where these sorts of concerns have been raised. And there's not really like a hard and fast rule on it. I think in general, is kind of encouraged to, if there are any concerns about that labeling, the labeling of the images in that data set, to then go away and maybe relabel it. And there are cases where groups have published studies using a data set, and then they've gone back and kind of relabeled it, rerun the model. So yeah, I think definitely that it's a very important consideration, because obviously the algorithm is going to be as good as the data. From the point of view of having information that's not necessarily available from the scan, sometimes that can actually even be helpful. Like because then you can actually define a kind of like stronger ground truth. Because let's say you have a picture that looks like a tumor on a chest x-ray, and then you send that away and you had like a definitive diagnosis from a biopsy. That can actually be quite helpful, because you are giving the algorithm an advantage in that the human interpreting it won't necessarily have that outcome known, but just by kind of reinforcing that ground truth, there's the potential for the algorithm to actually then perform even better if it's able to recognize some sort of pattern that enables that to be predicted.
And we saw in Mohan's presentation a lot of components that one can add to an overall system design with regards to safety critical tasks. So to what degree are you seeing a push for interpretability of AI solutions in medical applications?
Yeah, so definitely there is a kind of push towards it, and we want to kind of be able to identify that, and that's something that obviously regulators are going to value highly as well, because again, as the same sort of issues that you really don't want to be making mistakes. So when something does go wrong, you want to be able to interrogate it, and ideally you want to interrogate that like when it's still in a in silico context, and not when it's actually something that's being applied. And that is something that's been interesting. Like in a few of the kind of like landmark studies, there was a kind of study from Stanford a couple of years ago looking at chest X-rays. A big part of that study, the aim was to be able to diagnose based on the chest X-ray, like various different pathologies. But one big part of that study was a kind of heat map to show where the algorithm was looking, what areas of the chest X-ray were important for making the diagnosis. And so that sort of thing can be helpful as well.
Cool. I think we have one last question, which is if you look at some of the work that, for example, Alex presented from self-driving, it seems like this has been a huge amount of development in various computer vision techniques that are becoming increasingly kind of general purpose for different data domains. And so some of us are curious around how much of the innovations in computer vision in different fields can be directly translated over to medical imaging, or to what degree does the kind of data that you work with in medical imaging demand different architectures or different loss functions, et cetera, et cetera?
Yeah, I think on the whole, it seems that it is pretty transferable. So a lot of the big studies that have been done in medical imaging have not made huge numbers of modifications to kind of existing algorithms from other domains. And it tends to be, because there is a bit of a lag within this application of AI to healthcare, it tends to be the case that advances in AI algorithms that were done elsewhere are now just being transferred without too much modification to healthcare. And there's nothing that I'm aware of where anybody has kind of majorly redesigned kind of like algorithmic approaches to apply to healthcare. I think we're still at the stage where we can just apply the current computer vision technology, and that's not the limiting factor at the moment. The limiting factor is more things like data sets that we can then train the data on.
Great. Well, Chris, thanks a lot for a really interesting presentation, and thanks as well to other speakers. We've posted links on how you can get in touch with most of them, but yeah, feel free to reach out directly and follow them on Twitter. We're trying to do these maybe twice a month. As Nathan said, we're going to be announcing the next event quite soon, so keep an eye out on this Facebook group, follow us on Twitter if you don't, and sign up on our newsletter at London.AI. As mentioned by Nathan earlier, we do this to raise money for the RAAIS Foundation's COVID efforts. Special thanks to Amelia, Chris, Anna, and Mahadevan, who have donated so far. I've posted an additional link in the comments. So if you enjoyed the show, make sure to make a small donation. Everything helps. And to everyone, see you at the next one. Stay safe. And thanks for joining us. Bye.